Hey, welcome back, biophysicists, to another episode. Today, we are joined by Professor Pollak, a researcher at the Weizmann Institute of Science. We're going to be discussing his work along with Rajesh Dutta on what we can learn from transition path time distributions for protein folding and unfolding. Professor Pollak, thanks so much for being on the show.
Thank you. Thank you for your interest.
Yeah, I mean, why don't we go ahead and just dive right on in then? So what got you interested in transition path times, and what can we learn about them by studying them?
Well, it's an interesting story, actually. I read science, and this was 5 years ago where this paper came out by Newpain et al. That was from Woodside Group in Canada. And they had this they measurement of transition paths times for the folding and unfolding of two proteins, what they call a pinhole and a PRP protein. And it caught my eye because, first of all, there was their lead editorial by Woliness, and I know Peter. And secondly, I have been, during my life, doing work on rate theory, and so I felt that this was connected. And there was a real challenge in that paper. The challenge was that they measured, they had these transition path times, seeing, lines going from one side of the folded to the unfolded or vice versa. And they fit that to some theory. And from that theory, they reach a barrier height, which was of the order of what we would call 1 kT. In other words, just to put it in context, the typical barrier height for going from folded to unfolded or the other way around is of the order of at least 10. And this gave 1 or even a half. And this was not well understood. And Woliness pointed it out, and Woodside pointed it out, and this was left as a puzzle. And I was intrigued, what's going on? It can't be so difficult. And it didn't take me long to realize what actually was going on. What they were doing is the following. I don't know, I'll go a little bit into details into the experiment.
Yeah.
So the experiment is one when they take optical tweezers. Now, don't worry about the name optical tweezers. It's basically just taking tweezers. And what you do is you put a ball onto one side of the protein and put a ball on the other side of the protein. And now you can go and squeeze these balls or pull them apart. And what they do is they sort of play around with this until the energy for going from one direction to the other is more or less the same. The barrier, they're more or less of equal energy, the folded and the unfolded states.
Mm-hmm.
And then what they do is they have now a situation where they fix the distance between these two balls that hold the protein. And now they can watch how this distance changes, because when the distance changes, they feel it on their tweezers because something has moved.
Yeah.
And so you see how it stays for a while in one state, then goes to the other state, stays there for a while, and back and forth. And the time it stays in one state is sort of the time it takes it to move from, to change from the folded to the unfolded state or back. And then what they do is they say, okay, the distance, let's say, of these two balls is 3 for the folded state and 5 for the unfolded state. I'm throwing out just numbers.
Yeah, random numbers.
And so the distance between the two conformers, if you want, is 2 in this fictitious scale. And so they said, okay, let's start. And this is because they had a very sensitive apparatus, and believe me, that's really something. But so they take this distance and divide it into 3 parts: a half, 1.5, and 2. And they say, okay, let's look at these trajectories, if you want, of these balls the minute they start half, and then follow it till they reach 1.5. and stop. And then they repeat this experiment many, many times. And from this, they get this transition path, just time distribution, because each time to go from the half to the 1.5 takes different times.
So I guess quick question of clarification. If I start at 1/2 and let's say I go to 1, but then I go back to 1/2, do I reset my clock or do I just continue?
No, you just throw that out. You don't, that's
Yeah.
not a, they're looking at those paths, and this is an important point. They're looking at those paths that start at 1/2 and make it to 1.5, and the minute they reach 1.5, they stop. So they have what is called in the professional language, absorbing boundary conditions.
Mm-hmm.
When you reach the boundary, you stop the experiment, so to speak.
Yeah, your particle disappears, more or less.
You don't care what happens more. But now think about it. When we say that the barrier between the two conformers is, say, 10 kT, T being the temperature, K being Boltzmann constant. So when we say that the barrier is 10 kT, what we really mean is that when the distance goes from 2 to 3.5, the potential energy changes by this number 10. It goes from, say, 0 to 10. And then when we go to 3.5 to 5, it goes back down to 0. But in their experiment, they didn't start at 0 and go to 5. They started at 1.5, or they how did we say? We said 2 and 5. So they started at 2.5 and ended up at 4.5. I don't know if I got my numbers, if I screwed up my numbers here.
3 and 5.
I said 3 and 5. Right,
yeah.
right. So we said the interval was 3 and 5, and so in their experiment they're measuring between 3.5 and 4.5.
Mm-hmm.
They're not measuring from 3 to 5. Now 3.5 means that we've already climbed half of the mountain.
Yeah, I mean it could be the biggest mountain to climb, right? You know, the hardest step to take is the first. From the
is the first one. That's that, yeah. If you want to, okay. And so essentially, it is not surprising that they find a barrier height which is substantially smaller than the 10 of the full barrier height.
Because 1 kT is quite low in some regard.
Right. We'll get to that 1 kT soon. But this was my first observation on this. And this was published in a paper, I think it was in 2017. And actually, there's a nice story to this, because when I read the paper and I realized this point, I sent a letter to Science, trying to make this very simple point on their paper. Science rejected it. It didn't make it past the secretary. And this is a comment on the way science proceeds nowadays. But okay, so I wrote a paper. I did more than that in that paper. And this is published in PCCP also 4 years ago, I think. And then we said, okay, but let's look at this a little bit more carefully. And Rajesh has done a wonderful piece of work, because you see all the work that was done previously was basically done. My paper was published in 2016. All the work that was done, the analysis, the theoretical analysis of the experiments was done by taking models which are analytic.
Mm-hmm. And
models which are analytic means that your barrier profile is that of a parabolic barrier, -x². And that's a little bit primitive. And the second thing we asked ourselves is not only, so what happens if the barrier is not -x², but has a more complicated structure to it? And the second thing we asked ourselves is, so it's a beautiful experiment. What are we learning? What is this energy that they're measuring? Presumably this energy, if we change the endpoints, we get a different energy. So by changing the endpoints, we should be able to get the profile of the energy.
Mm-hmm.
And we know whether it's quadratic, parabolic barrier, quartic, hexic, or whatever it is. And so we said, okay, let's stop doing this analytically. Let's go to a numerical experiment. And the numerical experiment is using the same type of theory, which is a diffusion equation. And you can solve it on the computer. And of course, one difference between the theory that was used and when solving on the computer, the theory that was used open boundary conditions. In other words, they did not put an absorbing boundary at the endpoint or an absorbing boundary at the initial point. The trajectory in principle could go reach the endpoint, continue a little bit, come back, continue until it finally goes out and disappears. And so the first thing we did was we used this theory with the absorbing boundary condition and compared with their experiment. And lo and behold, what we found out, and this is the most important part, the wonderful agreement published between theory and experiment in 2016, the 2016 paper of Newpayne et al., is actually wrong because it was based on an open boundary condition theory. And when you use the absorbing boundary conditions, there's no good agreement. And not only is there no good agreement, but you find that the experimental distribution goes to much longer times than what you would expect from your theory, diffusion theory.
So I guess kind of one point of clarification for me then is, so the big difference between absorbing and the open boundary conditions is if you start a particle, like we said, at 1/2, and you stop the clock when it reaches 3/2.
1.5.
Yeah. If you have free boundary conditions, your particle can cross 3/2 and then come back again and recross, and that has an additional time that you're putting into the transition path. So
remember, we're looking at a very at time scales which are long compared to motions of the atoms on the protein. And you know, it's diffusing. It's like a drunkard. It's moving back and forth, back and forth, back and forth. It's a random walk. So there's no reason why it shouldn't. That's right. So there's no reason why it shouldn't, you know, go through, come back, go through, come back.
So I guess if it is just a biased random walk, if it crosses the 1.5 boundary, you stop the time, then it keeps moving. And every time it recrosses that boundary, you're adding that time to your ever-growing list of transition times?
That's if you're doing an open boundary theory. But if you're doing an absorbing boundary theory, you don't do that. So clearly, in your open boundary theory, you're getting a longer time distribution than in the absorbing boundary theory.
Because you're counting the same particle again and again and again.
That's right. And so what happens is that when you use the absorbing boundary theory, you do not get good agreement because your trajectories are shorter. And therefore, you find out that the experiment had a long time tail.
I see. So I guess, is it important then to, I guess, just kind of to play for some fun, could you do one end as a free boundary condition, one end as an absorbing boundary condition, or do they both need to be absorbing?
In the experiment, they're both absorbing.
I see.
Okay, so because you're throwing out trajectories that, let's say, start at one side and come back to that side. So the experiment that was done there is an experiment with absorbing boundary conditions on both sides.
Speaks to, you know, matching the correct experimental theory. So I guess behind kind of these models, there's a lot of different assumptions behind them. You know, we assume Markovian dynamics. We assume.
Let's first finish the punchline. Okay, because the punchline is essentially very simple. By doing the correct theory, what we learned is that the experiment gives longer times than the theory based on a simple barrier. In other words, there must be a trap which we do not have in our simple barrier theory. And lo and behold, the minute we put a trap in the reaction coordinates. Or in other words, instead of just simply having a single bell-shaped barrier, we go up, we have a small trap, and then we come down again. We could get good agreement between experiment and theory. And this is the not less important, the barrier height then for the transition path time distribution is not a half kT or 1 kT, it's 3 kT.
Much larger. Yeah.
Much larger. So 3 relative to 10 is something which our intuition can absorb.
Yeah, so I wonder if the barrier height is 3 kT then, and you do kind of have this metastable intermediate. Is it possible to observe that experimentally and really test this?
That is the challenge.
So you've in some sense,
we are now challenging. That's right. We're now challenging the experimentalists to go ahead and do these experiments more carefully and start looking at things, in a way which should tell us what the free energy profile really is. And
so
our experiment.
Oh, go ahead.
Go ahead.
I was just going to say, can you tell, I guess, basically whether or not you have like one rather deep well that's a metastable state or one that's very rugged in between? So you could have many kind of partially stable intermediates.
Everything is possible. And that's a question that we did not try to answer. All that we tried to show was that the experiment indicates a trap. And when we put that trap in the middle, we took 2 different shapes of traps, we could explain the experiment. And the experiment could not distinguish between the two. The experimental distribution, the noise on it, after all, its experiments, is such that you could not distinguish a quartic double well, quartic well on the top, or a triangular well, and so on. And I doubt that the experiment did that. There's a lot of noise in the experimental data. So that makes it very, so I cannot answer your question, and I doubt that the experiment will be able to answer the question, but I do think the experiment will be able to answer the question of whether there is a trap or not.
I guess, do you have any physical interpretation of what that trap might look like?
Yes. We're not the first ones who's, at the end of it all, let's remember the following. This whole way that we've been discussing is a huge simplification. We're taking this huge molecule, right? It's a protein, it's a piece of RNA, or
it's a free agent, yeah.
Okay, it has tens of thousands of particles on it. To go from one side to the other is not just going along one coordinate. There's a whole bunch of degrees of freedom there that play a role. We're simplifying it all in terms of saying, okay, all of these degrees of freedom are basically giving us a diffusion process over a free energy surface. But that's simplification. So the assumption that, and not only that, that simplification is really based on the assumption that you have a whole bunch of microstates that lead from the folded to the unfolded states and back and forth. So that there will be some microstates whose depth will be sufficiently large to trap is not unreasonable. And it has been, and other experiments, there's experiment by Eaton, I think, from 2015, which have been explained also talking about intermediate structures. Some people have measured, a colleague of mine, Gilad Aran, I think, has measured 4 or 5, has indicated his measurements using FRET, and it's a totally different experiment. Is first or resonant energy transfers, which FRET stands for. So the assumption, it's not outrageous to go and say there can be an intermediate. Your question was asked by the reviewers of our paper. They said, why don't we go and suggest what that intermediate is? And our answer to that was, that would be going too far. We just don't know. We're looking at a trivial model of one-dimensional model, and
Yeah,
the
if you
short
have
answer
many,
is
if
we
you have
don't
many
know.
degrees of freedom, there's many different possible right answers.
That's right. And we just don't know. However, yes, this is a question for future research. I mean, there are people who model these proteins using semi-empirical potential energy surfaces and running trajectories. And so that's another way of trying to look at the same problem. It's not trivial because you're looking at timescales which are microseconds. Microsecond timescales still take a very long time on a computer to go and get. So there are a lot of theoretical questions here, and there are experimental questions, but that's beautiful, isn't it?
Yeah, that's the rich treasure we're all after.
That's right.
So I guess it's kind of on the, I was just kind of curious reading the paper. It sounds like it isn't even really possible then to design a free energy profile that could exactly match the distribution times that you get from experiment. Or I guess it is possible, but there's just many, many ways in which to do it.
No. I beg to differ. You're making an experiment. Let's take the optical tweezer experiment of the Woodside group, where the reaction coordinate is essentially the distance between the two tethers holding the molecule.
Mm-hmm.
That's well defined. Okay?
Yep.
And now you have a one-dimensional coordinate, and you can average over everything else. And that's what gives you your free energy surface along that one-dimensional coordinate. And that free energy surface is well defined and has a value. It doesn't have different values. It has a profile, if you want. Quadratic, with a well, whatever it is, it has a profile, and that profile can be measured in principle. If you take a different reaction coordinate, for example, in the FRET experiments, Forster resonant energy transfer, what you do is you take two dye molecules, you put them on one side of the protein, you put them on the other side, and the probability of having a photon, or if you want a photon which is emitted from one dye or from the other dye, depends on the distance between the dyes. So you can imagine that by following such an experiment, at least in principle, you can also see a transition path. But now your reaction coordinate is a little bit different. It's not the two tethers.
It's not end-to-end distance, it's FRET.
It's not the end. It's the distance between the two FRET molecules, the two dye molecules that you're using. So different experiments can give you different free energy surfaces because it depends on what you're measuring. But with a given experiment, i.e. the optical tweezer model, there is a free energy surface there, and that free energy surface, we believe, will have a trap in the middle. Now, let's continue that. So suppose I take a molecule and I measure it with the optical tweezers.
And that free energy surface is unique too. That's also what...
That's right. It's unique to my choice of reaction coordinate. But now let's assume that I go and do the same experiment with FRET. Will I also see the trap? And the answer is probably yes, because the difference between the two reaction coordinates is not very big.
I guess in some sense you could try and think of like a Jacobian-ish type thing, because you're transitioning from one set of coordinates more or less to another. So you need to think about how they are influenced.
Yeah, but it's not easy to think about because there's too many dimensions. But if one experiment would show a trap, an intermediate, chances are that the other experiments would also show that intermediate. The exact shape of the intermediate may change from one experiment to the other.
So I guess, kind of one natural question, and you addressed it in the paper, and maybe you can speak some onto it, is, the multidimensionality of the problem, right? Like, you're reducing everything down to a simple one-dimensional coordinate, but in some sense, like you said, we have, maybe 100,000 different degrees of freedom. Why is my molecule? Why can I not just, take pathway 1 versus pathway 2? And how can we tell whether or not this is happening?
So it's, again, let's forget the transition path experiment. Let's just go back to the experiment of saying, I'm sitting in configuration A for some time, and then I'm jumping to configuration. I was sitting in the folded state, jumping to the unfolded state, back and forth.
Mm-hmm.
Okay, and I measure the mean time I stay in the folded state and the mean time I stay in the unfolded state.
Yep.
And now I repeat this experiment, but at a slightly different temperature. I increase the temperature, let's say. And what I will find out is that that mean time becomes shorter.
Naturally.
I plot that mean time as a function of the inverse temperature on an exponential scale, and I get the activation energy.
Mm-hmm.
So there exists a free energy of activation for going from one to the other. i.e., in some way or other, there exists a reaction coordinate along which there's a barrier whose height, there's a free energy barrier whose height is what I've measured experimentally.
So you're effectively just summing over all the different transition paths and all the different ways to get from folded to unfolded, and getting kind of an observed kinetic constant then.
That's right. And what you're doing is, as compared to the experiment of the rate of going from folded to unfolded, now you're looking at something which is a little bit different, which is the time distribution for going from the folded to the unfolded, which is a much shorter time because you're just looking at the actual transition from one to the other. But that time distribution can be then interpreted into a constant or into some range of constants, into a free energy profile. And that's what you're doing.
I guess it's interesting to think about, if I were to increase the temperature, I might be affecting the flux of one pathway more than the flux of another, say.
No. We're assuming that everything is equilibrium transitions, and therefore, there's what's called detailed balance or microscopic reversibility.
Mm-hmm.
Going from one there to there, it's more or less the same. But the question of the multidimensionality is sort of the old story about the economist and the physicist and the statistician who had to predict the results of a horse race. You know that one? So the economist made his economic calculations, said it's horse 1. And the statistician went backwards and said it's horse 2. And the physicist said, I solved a problem for a cylindrical horse. Okay, so that's what we're doing. We're solving the problem for a cylindrical horse.
Naturally. You always have to make good assumptions, though.
You have to simplify. But we learn along the way.
I mean, that's kind of how the science ball rolls, right? Little incremental processes. So I guess kind of one thing I was wondering too when reading this is, what level of experimental clarity, I guess, do you need to really be able to distinguish the difference between the different potential types? Because you've looked at, the difference between like a parabolic, a quartic, a hexic, and kind of one conclusion is, we can't really even distinguish between these different potential shapes with the experimental data. How fine-tuned do we really need to go before we can actually tease out the distinctive shapes?
So I think the answer to that is the following. Let's assume that the mean transition path time is a microsecond. Okay, and now we want to get the time distribution with some accuracy. And that means that we need so let's take this microsecond and divide it into 100 subunits, i.e. 10 to the minus 8 seconds subunits. And now I need to be able to observe enough trajectories in each one of these subunits to get a variance, if you want, of the result at a given time to be sufficiently small. And so the major part is not the number of trajectories, because that they do easily. You know, they're looking at single molecules, and so you repeat that experiment 10,000 times or 50,000 times. It's just a question of time, physical, the number of days you need to do it.
Grad students you have that are.
That's right. So in principle, you can collect that. The much more difficult part is getting it at 10 to the minus 8 second intervals, because that needs an enormous accuracy on your optical tweezers, and I don't think they have that. And so what happens is that you're not simply averaging over the mean time or mean number at a given time, but you're also taking a box in time, which is being averaged over. And that's the critical issue. Because if that box in time is not sufficiently small, you will not be able to say what the gradient of the potential of the free energy surface is around that place, because you have to see the differences. And that is where I think is the stumbling block of how far you can go. And that is why I don't believe that you'll be able, from the experiments, the way they're done today, distinguish between a hexic or a parabolic or a cusp-shaped barrier. But the long time tails do tell you that you can distinguish between a single bell-shaped function and one which has a trap in the middle.
It is quite interesting. I think that it's the kind of the long times. It's not even close to the mean that really tell you a lot about the actual free energy shape. You would think, oh, I'll take the average, I'll be fine. But it's really these deviations that are kind of the outliers that tell you a lot about it.
That is true on the one hand, but on the other hand, these are not the typical long time tails which go as t to the minus n. They are significant. When you look at our plots in the paper, you'll see that if the mean time is of the order of 1, by the time you're going to 2, the distribution of experimental distribution goes to, say, half of the maximum, while the theoretical distribution goes to 1/10 of the maximum. So it's a very significant result, and that is why the experiment can tell you that. If it was just a long time tail and the question of whether it's going as a power law or whatever, forget it. We wouldn't make it any heads or tails out of it.
Yeah, you can really see a larger difference than, I guess, to distinguish. So I guess, is there anything else that you wanted to kind of highlight or talk about that we haven't discussed so far?
No, I think this is, you know, there are other questions, which is a diffusion model really appropriate to this problem? That's a question we're working on. Why should it be appropriate? And yes, we would like to learn about, you know, what is really happening. What is the trap? Can we say something about it? But anybody else should go out there and do it. It's an interesting problem.
So are you thinking about adding in memory effects or multidimensionality to complicate it? Or is that the secret sauce you don't want to reveal?
No, there's nothing secret. I don't believe science goes on secrets. I don't think it's memory effects. Okay, I think that memory, yes, at the time scales we're looking at, it's not memory effects. It's much more the question of, there's an old paper by Van Kampen, there's a book by Van Kampen from 1983, which makes a connection between, and we write about it actually in our paper, between the diffusion equation and a model in which what you're doing is you're going from one microstate to the other in a Markovian fashion. And so the first thing I think to understand is the relationship between microstates along the reaction coordinate and the diffusion equation. And that's what we're looking at the moment.
I see. So I guess kind of my last question, is there anything particularly cool or any papers that you've read that you think are really fascinating here recently? Kind of the next brick in the scientific tower?
There's a series of paper by two colleagues called Berezkovsky and Makarov. And they have made various, for example, we relate to one of their papers, can one distinguish between a multidimensional distribution and a one-dimensional distribution? And I think that's a beautiful paper with a beautiful result. It's from 2019 or 20 or something of the sort. But in any case, anyone who's really interested in the theory of these things, go to the papers by some of them which we cite by Berezkovsky and Makarov, and I think you will learn a lot from them.
Yeah, I guess I'll try and link it in the show notes, but I think the papers you're talking about are the 2020 PNAS with Makarov and Satija and Berezkovsky, where they show
that's right. That's right.
So,
that's
yeah.
right. Yes.
All right. In that case, thanks so much for being on the show. It's been a lot of fun.
Thank you.